As I've already noted several times in this course, real bodies will emit and absorb less radiation than black bodies. So, the very simple expression, we could say that for a real body it will equal some constant which lies between 0 and 1 times the energy that would come off the black body, and that constant is known as the emissivity. In practice, the emissivity is actually a function of temperature, wavelength, the angle at which the radiation is leaving the surface, and the angle at which the radiation is reaching the viewer, and thus it shows complex behaviour. One of the things we're going to do is to actually deal with what we will call a grey body, and with a grey body we'll assume that the emissivity is a simple constant, so that we compare the energy emitted as a function of wavelength for a black body and a grey body. There is simply a constant multiplier which reduces the grey body curve compared to the black body curve. A more real surface would have some complex variation. With the example I've shown here with some wiggles around the grey body curve is not actually real data, but it's just showing that for a real surface there will be a more complex variation with terms such as the wavelength, and also in fact with the temperature. What I've shown on this slide is how the emissivity varies with the angle from the surface normal viewing for a black body, where things look uniform in all directions. A grey body, we have just said that epsilon will be taken as a constant, and then a typical non-metal or painted metal surface where the emissivity tends to be high, close to the normal, and then drops off as you go to angles approaching 90 degrees. For a bare metal, the emissivity tends to be relatively low, increases as you move towards the edge, and then drops off again as you go towards 90. Often data will be quoted for emissivity and will be normal data, so taken at an angle 0. A simple way of trying to interpret what all this means is if you looked at a black body sphere at a uniform temperature, then that black body would appear to be a uniform colour. If you looked at a bare metal sphere, then it would appear to be effectively brighter towards the edges, whereas a non-metal sphere would appear brighter towards the centre, because for the viewing angle it would be 0 degrees to the normal, whereas the edges would be 90 degrees to the normal. So overall I'm going to assume that I'm dealing with a grey body, so that the emissivity is a constant. Also in a grey body we assume that the absorptivity is equal to the emissivity. I'm going to be assuming that we're dealing with diffuse radiation throughout. Again, that's not in general true. And the other thing I'm going to assume is that this body is non-transparent, so the transmittivity is equal to 0. All of this represents a set of major simplifications, and at best will only be reasonable. However, without making these sorts of simplifications, the problems will become too complex for us to analyse in the context of this course. The other thing I'm going to assume at the moment is that there are no interactions of radiation with the atmosphere. Now, one of the things to realise then is that if we're dealing with bodies in general, then there'll be an amount of radiation that's coming into the surface. We call that the irradiation, or G. A fraction of that could be reflected, and that will be given by the reflectivity rho times G. Fraction could be absorbed, that's given by the absorptivity alpha times G, and then radiation re-emitted, which will be given by the emissivity times the black body term. And in addition, in the most general case, of course, some radiation could be transmitted, so that would be the transmittivity times G. And in terms of the incoming radiation, alpha plus rho plus tau equals 1. Now, I've already said that for a grey body I'm going to assume that tau is 0, and I'm also going to be taking that alpha is equal to epsilon. The other thing I should say here is that the sum of the reflected radiation plus the emitted radiation is known as the radiosity, and this is the total radiant energy leaving a surface. Now, to take this further, I'm going to try and consider a simple example of radiation exchange inside a furnace. And the furnace, I'm going to say, has a cubic cavity, 25 centimeters in each direction, and the side walls are heated by resistance heating elements that are within these side walls, and so that there's two side walls at a temperature of 1200 centigrade. And then if I say that the net heat flow from each of the side walls is 18 kilowatts, I want to estimate the temperature at the front, back, top and bottom of the furnace. So basically on the four other interior surfaces. So I'm going to need to consider radiation exchange between the side walls and the other surfaces. I'm going to assume that each surface is at a uniform temperature, that there are no temperature gradients as you come near to the corners. That's clearly going to be false. However, this is going to let me use the shape factor terms I've already dealt with. However, I've said that the emissivity is 0.75, i.e. when dealing with non-black surfaces, so how am I going to take that into account? In this particular case, for any surface, we'll have the irradiation G, the absorbed radiation, which will be epsilon G because we're treating it as a grey body, reflected term, which will be rho G, and emitted term, which will be given by the emissivity times the black body term, and those two together will add up to give you the radiosity. So if we then consider the net heat radiated from a surface with area AI, it will simply be given by that surface AI times Ji, the radiosity, minus Gi, the irradiation, and the subscript I in each case is indicating the fact that we're dealing with surface I. What I've then done is I've substituted the reflected term by saying it's equal to the radiosity minus the black body term, and obviously divided through by rho. But if I'm dealing with an opaque grey body, which essentially is what I've assumed, then rho I must equal 1 minus epsilon I, so I can replace the rho term here with 1 minus epsilon I. A little bit of rearrangement, I end up with the result that Qi equals epsilon I AI over 1 minus epsilon I times sigma Ti to the fourth minus Ji. So that tells me about the net heat radiated from one of the surfaces. This result is actually analogous with Ohm's law. Once again, I can say the heat flow is equivalent to the current. I can say that the driving potential or potential difference is sigma Ti to the fourth minus Ji, and then the inverse of this term will be the resistance, and I define that as a surface resistance. One thing you should be very careful of, this electrical resistance model is not compatible with the electrical resistance model that I previously used for conduction and convection. So I now have an electrical resistance model, but actually for the first step I can simply say, well, if the net heat flow from a surface is given by that expression, then I know that the net heat flow from one of my side surfaces is 18 kilowatts. I know all the dimensions, and I can work out that the radiosity for one of those side walls is therefore equal to 170.9 times 10 to the 3 watts per meter squared, or equivalently 170.9 kilowatts per meter squared. But that's only telling me about the energy flow from the surface. I also need to consider how the radiation is exchanged between two surfaces, and I can do this quite simply by saying that it is difference between the radiosity of the two surfaces divided by a term that I'm going to call the shape factor resistance, which is just equal to 1 over A1 F1 to 2 if the two surfaces I'm dealing with are 1 and 2. So that if I had just two surfaces exchanging radiation, I could just draw a simple series circuit. First resistance tells me about the surface resistance, the emissivity of surface 1. The second resistance tells me about how much surface 1 and surface 2 can see of each other, and the third one then tells me about the surface resistance or the emissivity of surface 2. So the endpoints of this network are actually the black body terms, and the radiosities are the potentials between the surface resistance and the shape factor resistance. And in that case, I have a very simple result that the net radiant exchange will be given by this expression just by applying Ohm's law. Things become more complicated if I have more surfaces. So if I had an enclosure with 3 surfaces, which is really the last case I can draw relatively simply, then this is what the resistance network would look like. each of these bits corresponds to a surface resistance for each of the individual surfaces, and then these are the shape factor resistances for going from one surface to another. The potentials at these outer points would again be given by the black body terms, and then the potentials at these points would be the radiosities. Now, to deal with this network, you have to use what's known as Kirchhoff's first law, which is simply that the currents flowing into a node, or equivalently the currents all flowing out of a node, must all add up to zero. Otherwise you would be creating or destroying current at a node. If you apply that, so this is for node 1, and simply going back to the previous slide, so what I'm doing is I'm saying the current flowing into this node is given by the potential difference between these 2 points divided by the resistance here. Similarly, in this case, potential difference between these 2 points divided by this resistance, and then the potential difference between these 2 points divided by this resistance. So I've just worked through that, and I get these 3 simultaneous equations by doing that at each of the 3 nodes. If you rearrange those equations a bit and use reciprocity, you can recast them in an apparently slightly simpler form, but actually these expressions are basically fully equivalent. But the latter form is slightly more convenient in the sense that you can say that for surface I out of a total of n surfaces, then this would be the overall expression that you have. This form of the equation is actually also allowing for surfaces that can see themselves. Coming back to my furnace problem, I actually have a total of 6 surfaces. I'm going to label the 2 sides which are heated as surfaces 1 and 2, then the front and back as surfaces 3 and 4, and the top and bottom as surfaces 5 and 6. I know the radiosities of the 2 side surfaces, namely, so I know J1 and J2. I also know the temperatures of those 2 surfaces, so I know T1 and T2. The other thing I know is that because I'm dealing with a cube, reciprocity therefore tells me very simply that F13 will equal F31 because all of the surfaces have the same area, so A1 and A3 will be equal, and I can simplify these relationships slightly. I can work out the shape factor resistance for any of the pairs of opposing sides very simply, because we already have seen the shape factor graph for that case, and I've done that here for F12, and you'll see from the graph that this gives us a value of F12 is 0.2, and by symmetry, in fact, all of the other shape factors in this particular problem are going to work out as 0.2. Although I could have shown that by going to this graph and working it out for the 2 surfaces that are perpendicular to each other from this graph. But whichever graph I use, overall I get the basic result that all my shape factors in this particular problem are 0.2. Hence, if I can consider side 1, I've got this following expression relating the radiosity I've already calculated to the unknown radiosities J3, J4, J5 and J6. Simple symmetry considerations for this particular problem will tell me that J3 must equal J4, must equal J5, must equal J6, because all the other surfaces are effectively equivalent to each other. So putting all of that together, that tells me that the radiosity J3 must be 189.0 times 10 to the 3 watts per meter squared. And if I now consider the equation for side 3 with the unknown temperature T3, then I can work out that the temperature T3 and therefore the other temperatures of the other sides must be 1355 Kelvin or 1082 centigrade. This is a particularly simple example because of the high degree of symmetry, and more generally I might have had multiple equations that I had to solve via either Gaussian elimination or Gauss-Seidel iteration.